Hello again. For this video we're going to be talking about related rates, which is section 3.9. And what related rates are is it's a class of problems where you have multiple rates of change bound together or related to each other through one or more common equations. One of the most basic examples of that is, say you had a triangle with one side growing and one side shrinking. We'll say that this height here is shrinking by 1 foot per second, and this other side is growing by 2 feet per second. Then what I would be able to do is I would be able to calculate the rate of change of the area for this triangle. To do that, I'm going to need to lay down some additional information, so I'm going to ask, find A prime, the rate of change of the area of the triangle, when the height is 4 and the width, or the length of the base, is 3. And how I find these is, well, I find the area of a triangle, which is the area is equal to 1/2 base times height. And then I take a derivative with respect to time, because it's a rate of change as time occurs. Take the derivative with respect to time, so I'll have A prime, or dA dt if you prefer, which is equal to 1/2 times, and here I have two variables, so I'm going to do a product rule between them. I'm going to have B prime times H plus B times H prime. And then after I take my derivative, I'm going to plug in as much information as I can to try to solve my problem. I'm trying to find A prime when my height is 4 and my base is 3. But the B prime here, that's the rate of change of the base, and the base is increasing at 2 feet per second. So this is going to be 2 times 4 plus 3 times the rate of change of height. It's shrinking by 1 foot per second, so I'm calling it -1 feet per second because it's changing in a negative manner. So the rate of change of my area is in fact 1/2 of 8 minus 3, or 5/2. And these problems can be incredibly diverse. So I'm going to do some more examples. We'll have one. So here we have a mysterious stranger, 1.8 meters in height, is walking away from a street light, 6 meters in height, at a rate of 1/2 of a meter per second. And I want to find the rate at which the shadow cast by the stranger grows when they are 3 meters away from the street light. Now what we want to do, first off, for all of these problems, is we want to draw a picture to help us determine what kind of a function we're going to need to bind the rates of change together. So I have my mysterious stranger and my pole, and I've got 1.8 here, definitely not to scale. The shadow casts a light, and the stranger casts a shadow here. So I'll label the shadow with the cursive S, and I'm looking for the rate of change of S, correct? I want to find the rate at which the shadow is growing. So the distance the stranger is away from the street light is going to be, I'm going to call it x equal to 3 meters. And I know that dx dt, the rate of change of this distance, is going to be 1/2, because he's walking away from the street light at 1/2 meter per second. Now somehow I have to get an equation binding together ds dt and dx dt. And the way I'm going to do that is I'm going to use similar triangles, because I have one really big triangle from the street light all the way over to the end of the shadow, and then I have a really small triangle from the stranger to the end of his shadow. So let's see. So I'm going to have 1.8 is to 6 equal to, small to big, I'll have S is to the whole big side is x plus s. I don't want to plug in the 3 yet because I only want to plug in x equals 3 when I'm looking for after I've taken my derivative. I plug in nothing until I've taken my derivative first. Before then, everything is a variable, unless it's already constant. For example, my stranger, he's not changing in height, hopefully, and my street light is not changing in height. I can simplify this a little bit. I have 18 divided by 10 all over 6 equals s over x plus s, which means I have 3 over 10 equal to s over x plus s, and I'll cross multiply to get 3x plus 3s equals 10s, or 3x equals 7s. So now that I have the simplified version, my derivative is going to look a lot nicer than if I had tried to use the quotient rule above. Take the derivative with respect to t, and we'll get 3 dx dt equals 7 ds dt. But dx dt is equal to 1/2, so when x equals 3, I actually don't have to plug anything in for this problem. So it looks like the shadow's rate of change is independent of how far away it is. Or basically, since the dx dt is a constant rate of change, I have 3 times 1/2 equals 7 ds dt. I have a constant rate of change for the length of my shadow, and I end up with ds dt equal to 3 divided by 14. And this problem was given in meters per second. For a more geometric example, we have that pink slime, totally edible, is being added to an inverted conical tank of radius 2 meters and height 5 meters at a rate of 40 cubic centimeters per second. And we want to find the rate of change of the depth of the slime when the depth of the slime is 2 meters. So, starting with a picture, I have a conical tank. The radius is 2 meters, and the height is 5 meters. And I'm just dumping this goo in, so that's a dv dt of 40. Notice here that the 40 is in centimeters, cubic centimeters per second, but the dimensions of my cone are in meters. So what I should do is I should normalize all of my units before I start doing my problem, or I'm going to get some weird numbers in the end. So I'm going to switch to centimeters because it'll be easier than trying to change the 40. So instead of 2 meters, I'll have 200 centimeters, and instead of 5 meters, I'll have 500 centimeters. And in here, I'll have some amount of pink slime. Now, I want to find the rate of change of the depth of the slime. So I'm going to need a variable here describing the height of this slime in here. And I want to know this when the depth of the slime is 2 meters. So, the volume of a cone is 1/3 pi r squared times the height. But I actually have 2 cones here. I have the big cone, which is the whole tank, and I have a smaller cone which is composed entirely of pink slime because it takes the form of the shape that it's in. So what I need to know is the volume of the pink slime instead of the whole tank. And the volume of the pink slime is changing. So for this I want to take a derivative. But wisdom of the ages, since I have a cone problem here, I'm going to want to eliminate one of these 2 variables if I can. I want to do this for all of the problems, eliminate as many variables as I can, but sometimes I just can't. And the idea here is the pink slime cone down here is similar to the big cone that makes up the tank. It's just smaller. So I'm actually again going to use similar triangles for this problem. Here I have a height associated with the slime, and I have a radius associated with the slime. But this triangle that I've drawn down here is similar to the triangle that makes up the bigger cone. So I have that r is to 2 as h is to 5. Now, since my question is asking stuff about the height, and I have information about the height I want to eliminate the r since I have the height. So I want to solve for r. R equals 2h over 5, and I'll use that information to plug into my volume. I don't necessarily have to do this step right now, but it's generally a little bit better to do it now because it'll save us some time. So if I make the substitution, my volume is equal to 1/3 pi 2 times the height of the slime squared times the height of the slime, or 1/3 times pi times 4 over 25 times h cubed, which is 4 pi over 75 h cubed, which is much easier to take a derivative of. So, with respect to time, I have my dv dt equal to 4 pi over 75 times 3h squared times dh dt. Now, I want to know the rate of change of the height, and I already know that the dv dt is equal to 40. So what I need to do now is plug in my height of 2 meters, or since I have units in centimeters, I should use 200 centimeters. So I have 40 equal to 4 pi over 75 times 3 times 200 squared dh dt. And I want to solve for that dh dt. dh dt equal to, do this carefully, 10 times 25 divided by pi and divided by 200 squared. And this is equal to 250 divided by 40,000 pi, which is equal to 1 over 160 pi. And these units are centimeters per second. Another geometric example. Suppose a spherical balloon is being inflated at a rate of 8 cubic centimeters per second. Find the rate at which the surface area is increasing when the radius is 15 centimeters. This one's a little weird because we don't necessarily have an equation directly linking the volume and the surface area at the same time. But we'll go ahead and draw our picture. I want an r equal to 15 in the end, and the rate of change of the volume is going to be 8 cubic centimeters per second. And the volume of a sphere is 4/3 pi r cubed. But the surface area is 4 pi r squared. So what I'm actually going to do in this case is I'm going to take the derivatives of both of them, because I have information about the rate of change of the volume, I want information about the rate of change of the surface area, and both of them are going to depend on the rate of change of the radius, as we'll see. So v prime, this is going to be equal to 4/3 pi times 3r squared r prime. And this is always equal to 8, which means I have 8 equals, these 3's cancel, I have 4 pi r squared times r prime. Meaning 8 divided by 4 pi r squared is equal to r prime. So when r is equal to 15, I have r prime is equal to 2 over 225 pi. And I want information about the rate of change of my surface area, so I'll find SA prime. And that's equal to 4 pi times 2r, r prime, So when r is equal to 15, I'm going to have the same r prime here. I'll have SA prime equal to 4 pi times 30 times 2 over 225 pi. Those cancel. I have SA prime equal to 16 over 15. And this is in square centimeters per second. For the final example, we have a bit of a construction problem. Wow, that's quite a wall of text that suddenly appeared. A winch at the top of a 30-foot building is used to hoist a pipe of the same length to a vertical position alongside the building. The cable is attached to the end of the pipe that is furthest away from the building, and it is pulled in at a rate of 4 inches per second. We want to find the rate at which the angle between the pipe and the building changes when that same angle is pi over 6 radians. So, as always, I can't do anything without a picture. So let's have a building. That's 30 feet. And there's a pipe that I'm lifting up to be alongside the building. And this pipe is connected by a cable that's being pulled in at a rate of 4 inches per second. Now I have the same problem I did last time. I have feet over here for the lengths, but I have inches for my rate of change. So I'm going to change this actually. Instead of having a 4, let's call this 1/3 of a foot per second. And I want information about the angle between the pipe and the building. That's this guy right here. So somehow I've got to combine all this information into, hopefully, one equation. More if I need to. Fortunately, there is just such an equation, and that is the law of cosines. If I have any triangle, A, B, C, and I have little a little b, and a little c, then we have the following modification of the Pythagorean theorem, and that is little c squared, the length of the longest side, or the opposite side of c, is equal to a squared plus b squared minus 2ab cosine of c. And I use this, so if I know two legs and an included angle, I can find the length of the third side, because that'll be the square of the first leg plus the square of the second leg minus 2 times the product of both legs times the cosine of the included angle. So adapting this to my problem, I'll call x the amount of cable I have between the building and the pipe. I'll have x squared is equal to a squared, but that's just 30 squared, plus b squared, which is 30 squared again, minus 2ab, which is actually 30 squared again, times cosine of the included angle, cosine of theta. Now, I want to take a derivative, like all of my related rates problems, since I have an equation. I'm going to get 2x, x prime, equals 0 plus 0, minus 2 times 30 squared. Derivative of cosine is negative sine times theta prime. Simplifying this a little bit, I have 2x x prime equals positive 2 times 30 squared sine of theta, theta prime. Now what I wanted to know was the rate of change of the angle between the sides. I wanted to know theta prime when theta is equal to pi over 6 radians. If I try to plug in all the information I have, I'll have 2, I don't know the length of x, but I do know the rate of change of x. That is 1/3, negative 1/3, because it's a shrinking value. I missed that when I drew my picture. Since this pipe is going up towards the building, the distance between the building and the pipe is shrinking. So this is actually a negative rate of change for that side. This is equal to 2 times 30 squared sine of pi over 6. And I have left the theta prime, which I want to solve for. Now I have this x left over, and I'm going to have to use my original equation up here to solve for my x value. Since I have x squared is equal to 30 squared plus 30 squared minus 2 times 30 squared times cosine of pi over 6. Let's see if I can simplify that a little bit. Cosine of pi over 6 is the square root of 3 divided by 2. So x squared is equal to 2 times 30 squared minus 2 times 30 squared multiplied by root 3 over 2. So x squared is equal to, if I factor this, 30 squared times 2 minus the square root of 3. That leaves me with an x equal to the square root. I have a positive or a negative here, but I'm just going to toss the negative because that's silly. I don't want to have a negative rope length. 30 squared times 2 minus root 3, or I'll have 30 times the square root of 2 minus root 3. It's always a good day when you have a square root inside of a square root. So bringing this guy back down, that means I have 30 square root of 2 minus root 3 times negative 1/3 equals 2 times 30 squared times sine of pi over 6. That is 1/2 times theta prime. So solving for theta prime, I get negative 2/3 times 30 square root of 2 minus root 3, all divided by 30 squared. Or if I simplify it a little bit more, theta prime is equal to negative 2 root 2 minus root 3 all over 90. Or even further, negative root 2 minus root 3 over 45. And that is radians per second. All of these related rate problems should basically be treated the same way. You should read the question, maybe read it again, draw a picture, and label your picture with your variables so that you have a better idea of what you're going to want to set up for your equation. But the equations could be very diverse, and sometimes you'll have to solve these problems in unpredictable ways. The next video is going to be about approximation. We're going to use the derivative to approximate values to simplify our calculations a little bit.